Large language models, or LLMs, have revolutionized artificial intelligence, particularly in software engineering, where specialized versions called code LLMs are helping developers write, debug, and optimize code at an unprecedented scale. These models are trained on vast amounts of data and can generate code snippets, fix errors, and even suggest improvements, making them a staple in modern development workflows. However, despite their impressive capabilities, code LLMs aren't perfect. They often produce outputs that are incorrect, insecure, or unreliable, which can lead to serious issues like software bugs, vulnerabilities, or even system failures in critical applications. This research paper, titled Risk Assessment Framework for Code LLMs via Leveraging Internal States, addresses these challenges by proposing a new approach to make code LLMs more trustworthy. The authors, Yuheng Huang from the University of Tokyo, Lei Ma from both the University of Tokyo and the University of Alberta, and Kizaburo Nishikino and Takumi Okazaki from Fujitsu Limited, draw inspiration from how the human brain detects its own mistakes. Just as humans have an internal sense that flags errors unconsciously, the paper suggests we can analyze the internal states of LLMs to identify risky code outputs. The core contribution is a framework called PT Trust, which is designed to integrate seamlessly into existing software company infrastructures. PT Trust operates in two main stages, mirroring the pre-training process used in LLMs themselves. In the first stage, it performs unsupervised pre-training on a large-scale dataset of unlabeled source code. This step helps the framework learn general representations of the LLM's internal states, such as the hidden activations or intermediate outputs that occur during code generation. By exposing the model to a wide variety of code examples, PT Trust builds a broad understanding of what typical, safe code looks like at a fundamental level. In the second stage, PT Trust uses a smaller, labeled dataset to fine-tune a risk predictor. This labeled data consists of code examples that have been manually annotated to indicate whether they contain risks, like security flaws or logical errors. The risk predictor then learns to classify the internal states of the LLM as high risk or low risk based on these annotations. This two-stage approach makes PT Trust efficient because it leverages the power of unsupervised learning for the bulk of the work, while using targeted supervised learning to achieve precise risk detection. One of the key strengths of PT Trust is its ability to perform fine-grained risk assessment, right down to the level of individual lines of code. For instance, if an LLM generates a function with a potential vulnerability, PT Trust can pinpoint exactly which line is problematic by analyzing the corresponding internal states. The paper demonstrates this through experiments across different programming languages, such as Python, Java, and C++, showing that the framework generalizes well beyond a single domain. In their experiments, the authors tested PT Trust on various software engineering tasks, including code completion and bug fixing. The results showed that PT Trust could accurately detect risky outputs with high precision, often outperforming existing methods that rely on surface-level analysis of the generated code. Moreover, the features extracted from the internal states proved to be intuitive and interpretable. For example, certain patterns in the LLM's activations might indicate confusion or uncertainty, which users can easily understand and use to build trust in the system. This interpretability is crucial because it allows developers to not only flag risks but also understand why a piece of code might be unsafe. Imagine a scenario where a developer is using an AI tool to write code for a financial application. PT Trust could highlight that a specific line of code has a high risk of causing a security breach, based on the model's internal signals, and provide explanations that make sense to the human user. The paper also emphasizes scalability and practicality for industry use. Unlike previous approaches that were limited to specific subdomains or required massive computational resources, PT Trust is designed to work with existing LLM infrastructures. This means software companies can adopt it without overhauling their systems, potentially integrating it into tools like code editors or CI/CD pipelines. Furthermore, the authors connect this work to broader themes in AI, referencing the Bitter Lesson by Richard S. Sutton, which argues that leveraging computation is key to long-term progress. By applying computational methods to analyze internal states, PT Trust exemplifies this idea, pushing forward the reliability of AI in real-world applications. Overall, through these innovations, PT Trust represents a promising step toward making code LLMs safer and more dependable, ultimately fostering greater adoption in software development where trust is paramount. The framework's ability to generalize across tasks and languages, combined with its interpretable outputs, could significantly reduce the risks associated with AI-generated code, paving the way for more secure and efficient programming practices.